Hi, from today, we're going to move on to statistical process control. So this is the most important techniques in quality management. It is originally pioneered by Dr. Schwartz, okay, who is the teacher of Dr. Deming. And it was later embraced by the manufacturing context, later service industry, and then even in the medical context. Okay, it's a tool where you can use to monitor your process. Okay, most importantly, it helps you identify what is the underlying causes for process instability. Okay, so even more important thing is that it is pretty simple to usually tells managers to take corrective actions to the system. Okay, so the tool is a tool will be very valuable. It can directly tell you there is something need to be done immediately. Okay, that is one reason why the statistical process control is very powerful and useful in a lot of context. Okay, so if you look at this chart here, this is the bare bone structure of SPC control chart. So you usually see there are upper limit and a lower limit. Okay, so these are not specification limit. These are the upper control limit, lower control limit. So when something falling outside of the control limit, that usually means there's something is happening on your process. You need to stop and investigate. Okay, and there's a center line, which this is the process average, and then you're trying to plot these dots as it happens. And one thing you don't want to see is a dot falling outside of the control limit. If it's falling outside of the control limit, that means you need to stop. Okay. The key idea behind the control chart is the outlier detection. So statistically, you understand that there's very little chance that an observation will be falling outside of 3 sigma, 3 standard deviation away. So if you look at this particular distribution with average of 100, standard deviation of 10, if you're plotting 3 standard deviation range before and after the average, we see that 70 is going to be the control limit, a lower control limit, and 130 is going to be upper control limit. So anything falling outside of these two numbers will be considered as outlier, meaning it has very little chance to see things like this large or even things like this small, given the inherent variability. Okay, so I hope you do understand what this means. We've done a lot of training just so that I can help you understand what this is about. Okay, it is time for us to take advantage of those understanding. So again, how do you plot a control chart? So this is underlying theory or rationale for the control chart. So this is what you have seen the previous slide. I rotate it, and this is how a control chart is made. So the average here stays as a center line, and the upper control limit stays as upper control limit, and lower limit stays as control limit, lower control limit, and then this is what you're seeing from here. So all these, I'm seeing 17 observations here, 17 observations here. All 17 observations are staying within the 3 standard deviation range. See, this one, if you take it to plot it here, it's going to be somewhere here. If you take the second observation, it will be somewhere here. All of them, at least from this drawing, are falling within the control limit. Okay, so convenience of plotting the number on the run chart like this is that we can compare each observation, and we can actually reference each observation back to its time of its occurrence. So sometimes time information can be critical in helping you understand what actually happened. Okay, so for example, if you're plotting this as, I don't know, maybe GDP, right? You see the certain point has especially low. The moment you know this is about 2008, you can understand, oh, this is where the recession happened, right? So sometimes you can apply the time information wisely to try to figure out what happened here. So that is why we are plotting this in this fashion. This is called a run chart. Okay, I mean, in our context, this is called a control chart, but it has different name called a run chart or time series plot. Time series plot. Okay, even CDC, Center for Disease Control, they also use this way of plotting the data. Obviously, they need to track number of the number of infectious disease that is happening on a weekly basis. Right? They need to know whether this week we had an abnormally high number of infectious disease. If that is the case, they need to take some corrective actions, right? So that is what the control chart is look like. Another important thing the control chart can help us is to help us identify whether a assignable cause or the common cause is happened during the process. Okay, so if you look at the rationale here, the variability is a part of any process. For any process, you will have to expect a certain level of variability. So if you believe that Costco is so good in helping customer doing checkout, they're so swift, they're so fast, but if you look at the number of times they're helping customer check out per item, you will still see the certain variations from worker to worker, from item to item. Okay, it could be because of the operator who's new. It could be because of customer who's very picky. It could be just very bulky item. It takes time to do the scanning. So you would expect a lot of different variability or variations in the process. So we divide variability into two different types. One is called special causes. The other one is called common causes. So starting from the common causes, it is the variability that is caused by the process itself. It is inherent to the process, meaning that if you're using a very low efficiency equipment, you should expect certain number of variability. That is it. Okay? But the special cause is that when something happens that beyonds what you normally expect from the process, and then you can actually assign the cause to a specific person or a specific machine or some other factors. Okay, so for the line manager or manufacturing manager or operators, in order to be helpful for them, it is important to identify the special causes rather than the common causes. Okay, so understanding common causes will help a manager to be more generous toward his workers, but understanding the special causes can usually help a worker or manager to identify whether something extraordinary actually happened or not. If you look at the visual display, and the special cause means something happening outside of the control limit. Okay, so whenever something happening outside of the control limit, then we can stop and investigate whether a special cause has happened or not. So if you recall, second problem of homework number 4, I was trying to help you to think about these two different types of causes. We have briefly explained in chapter 5 the process focus. The Deming's experiment is used, actually, the experiment is actually used to demonstrate these two different type of causes. Okay. When a process is in control or under the control. So by looking at this run chart or control chart, the first is, of course, no point is outside of the control limits, right? Like this is stable and this is everything within control. The number of points above and below the center line is about the same. So meaning it's truly random, right? This up and down pattern, there's no traceable pattern you can see here. There's no, seasonal thing exists here, right? There's no seasonal thing exists here. It's just truly random, up and down. And number 3, the point seems to fall randomly above and below. I just mentioned this, right? And most points, but not all, are near the center line, and only a few are close to the control limit. So here, not many are staying outside of second standard deviation distance here. Only this one is staying outside of a second standard deviation. It is closer to the upper control limit. All other things are actually embracing this central line. Okay, there's no traceable pattern, and there's nothing too close, nothing too far from the central line. And this is one thing we would like to expect by just looking at it. So in fact, the identification of out of control takes some experience to learn. Okay, of course we're going to discuss when we're going to eventually discuss how to detect whether a process is out of control. But I just like to share upfront. It takes some experience and stat knowledge to effectively identify whether a process is in control or not. Okay, so let's take a look at the pattern here. So you can observe many different patterns. They may signify different things. So point outside of control limit and sudden shift in process average. Like here, there's a sudden shift, right? Sudden shift. It's very low to very high. There's a sudden shift in here. And there are some cycles, cycle, right? A cycle means something like this, which we don't quite see from this particular drawing. And then there's some trend. So here is upward trend, and then hugging the center line, like this type of trend. You're hugging the center line, and sometimes you see something like hugging the control limit. Okay, hugging the control limit. Let me show you one by one. So they all imply some underlying causes. You can attribute those causes to machine, operator, material, schedule, policy, and so forth. Okay, yeah, machine made a mistake, operator can make a mistake, material maybe not correct, and sometimes schedule also have something to do with the non-conformity. So for example, maybe afternoon 1:30 p.m. workers can be very sleepy, right? After the lunch, could be sleepy. That could be a cause. So all of them, by just looking at the control chart, you should be able to, if you're an experienced manager, you should be able to tell the story behind each charts. So for number one, it's 1 point outside of control limit. You can tell this easily. And other than that, all of them are staying within control. In this case, ideally the line should have stopped here. Okay, once you spotted the first one, you should have stopped your line and do the investigation. But if you are looking at this retrospectively, and you should be able to go back and take a look at the record that is associated number 4 and should be able to identify what is happening by the time. And this is a shift in process average. Obviously, the last range of observation here, they are staying above the center line. Okay, they're staying above the center line, meaning it's likely that the process average has increased. Okay, so if you're seeing something like this, that implies your process average has shifted. And here is a sudden shift in the process average. You see sudden jump from here, low point to high point to low point. I'm sorry, the high point to low point. And here again, the low point all the way to high point. You see the sudden shift in process average also helps you identify, also help you to stop and think what actually happened here. Okay, sometimes you see cycle like this, see some cycle, especially if you're seeing this Monday, Tuesday, Wednesday, Thursday, things like that. And if you think about that, what could be the reason that contributes this Monday, Wednesday effect and Tuesday, Thursday effect? Sometimes you're using immature workers Monday, Wednesday, mature workers on Monday, Wednesday only, immature workers on Tuesday, Thursday only. These could be the underlying reason that contributes to this type of shape. Okay, and then again here, no dots are too high or too low. Okay, this is indication that your control limit may be wrong. Okay, because these are too high. So maybe it implies that you have wrong calculation here. So here, hugging the control limit, these are not staying within close with the central line. Instead, they're staying with the upper control and lower control. So I need to stop here.